So I've listed the homework at the top. This is the chapter on carbohydrates. I guess commonly we refer to carbohydrates as starches, but they also include the sugars. Really, carbohydrates are polymers of sugar molecules, and we call those polysaccharides. And so in order to understand carbohydrates well, I think it's easiest to work with Fischer diagrams. Fischer is the scientist who spent a great deal of time understanding the structures and the chemistry of carbohydrates in sort of the middle 1800s, actually. So what we're going to do is review Fischer diagrams. So first of all, you remember we have perspective diagrams. Perspective diagrams, we often draw them like this. We'll take a line for a bond and a line for a bond. We have wedges and we have hatches. And this is going back and this is going forward. And these two are in the plane of the paper. Okay? So in plane is maybe the way to say it best. And so we give ourselves this drawing style to help us get a grasp of the three-dimensional structures of molecules. So when we're doing a Fischer diagram, what we're doing actually is we don't have actually any of the atoms in the plane except for the central carbon atom. That's this guy right here. So we'll draw it like this. Oh, did it backwards actually. We'll draw it like this, and then there's a central carbon, and there's a wedge like this, representing atoms on the side. And then hatches like this. So what this means is that these groups are coming forward from the carbon. The carbon is in the plane of the paper, and then these hatches mean they're backwards. Okay, so these are back, and these ones are forward. So what Fischer did is he reduced that down to this kind of structure. So it's implied in a Fischer diagram that the atoms on the sides are going forward and the atoms top and bottom are going backwards. So let's talk a little bit about determining R and S, and it's really actually not that important for this chapter. But I thought this was a good place to review R and S. So let's start with a structure that looks like this, Br, right? And then we have H, and then we have CH3, so a methyl group, and a CH2CH3. Now, what we want to do, and this is the same process you go through whether it's in a Fischer diagram or in a hatch and wedge type perspective diagram, you assign priorities based on atomic numbers. So the bromine that's on the left is the highest priority, this, right? And then the CH3 is the, well, let's do this. The easy one is hydrogen, so this is 4. You have a hydrogen, that's almost always lowest priority. And then second priority would be the lower CH2CH3, because even though these are both carbons that are attached, this carbon has another carbon attached to it. So that gives it a higher priority. When there's a tie, you look at the next atom out, and since one of the atoms it's attached to is a carbon, it beats this one because this has 3 hydrogens on it. So this would be number 2. And really, you only need to assign 1, 2, and 4 in order to make this work, because 3 by default will be the one that's left, right? Okay, so here we are. There's 3. Now, this is rotating in this direction. So in a perspective diagram, when it rotates to, I guess, the counterclockwise direction, this is what we would call the S rotation direction. So this is what I'm going to say is this. This looks S, because it looks like a counterclockwise rotation of the groups. But the thing you have to remember, and this is important for Fischer diagrams, this group is in the front. And this happens a lot in these kinds of Fischer diagrams. And I'll show you some examples of like small carbohydrates in a second, so we can practice with the carbohydrates. But that is the 4 group in the front, and if you remember, it has to be in the back in order to sort of standardize the way that we talk about the rotation of the groups or the order of the group. So it looks S, but R. The 4 group is in front. So that means it's actually R, because in order to put the 4 group in the back, you'd have to flip the molecule around, and then the direction of rotation would be in the other direction. So it looks S, but 4, that's a 4. I can't quite read it, can you? Make it a little bit bigger, I could write it clearer maybe. The 4 is in front, so is actually R. Okay. Okay, so now let's look at a small carbohydrate. A small carbohydrate would look like glyceraldehyde. This is known as D-Glyceraldehyde. And I'll talk about the meaning of the letter D in a second. But this is the smallest of the sugars. So what I have up here is CHO. This, you just have to get used to this idea because it comes up all the time. The CHO is actually the aldehyde functional group. So it really looks like this. And then I still have the H and the OH and the CH2OH like that. Okay, so now we're going to assign priorities and then determine the direction of rotation. And almost always in a Fischer diagram, on the horizontal bar, one of the groups will be hydrogen. So this is why I talked about, this is the number 4 group. This is why I gave that example above. The 4 group being in the front means the observed rotation on the paper is not the actual rotation in the molecule. Okay, so what's the next highest priority group? Or the highest priority group, I should say. That's oxygen. That's number 1. Now we have a C double bonded to an O, and then a C bonded to an O, and then 2 H's. So the C double bonded to the O acts like this carbon is bonded to 2 oxygens. Now, when we did this ranking before, what we would do, we would say, okay, I have the carbon, and then down here I have the carbon as well. So I'll do that in red. Okay, and then on each of those, I have 3 different bonds. I have oxygen, oxygen, and hydrogen. And on the red one, the one I've done in red, I have oxygen, hydrogen, and hydrogen like this. Now, when I do that, right, what I'm doing is these groups, these oxygens, oxygen, hydrogen, the order that they're put in here is very specific. They're in order of descending atomic number. So oxygen, oxygen, hydrogen, not hydrogen, oxygen, oxygen, or oxygen, hydrogen, oxygen. It has to be specifically in highest to lowest atomic number order. So that's what's going on down here. This is C, and this is bonded to the O. That's this O here, and then H and H, okay? So what we do is we look at the first point of difference, and in this molecule, the first point of difference is here. I have an oxygen and a hydrogen. So that's why the aldehyde functional group in this molecule gets the number 2 assignment in terms of priority. So then by default, this one's number 3 because I've already designated number 4. Now I can assign the stereochemistry, or the specific I won't say specific rotation, but I can give the configuration for this carbon that's here as going in this direction. So I'm going 1 to 2 like this. Okay, so that looks like S, right? So this looks S. But, right, H is in the front. The 4 group is in the front. Is in the front. And so you'll see this a lot in carbohydrates. You'll look at the assignment of priorities And then once you've determined what the assignment is, usually there's a hydrogen along one of the sides, and that tells you that what you're actually assigning, the actual molecule, you'll have to reverse the configuration. So this is actually R. Like that. All right. Next thing to do is to talk a little bit about how we manipulate Fischer diagrams. And this isn't really so much for this class as it is more for my Chem 28 series students. That's a little bit higher if you're watching this randomly for some reason out of the internet. That's my higher level organic chemistry course. Just a couple of things about transformations. And I'm going to do it like this. I'm going to go 1. Let's do 2. And then 3. And 4. So I'm going to randomly make up a molecule. And those are the assignments. So whatever those groups are, let's say they're 1, 2, 3, and 4, like that. So my number 1 group is at the top. It's going this way. But this group is in the front. All right, so this is S-like. And so this is equal to R. Now, look what happens if you take and you turn this 90 degrees. So I'm going to turn it like this. It doesn't matter 90 degrees in which direction, but I'm going to turn it like, let's say I'll put the 1 here. So that means I'm rotating it clockwise. I put the 2 here. That would put the 3 here, and then the 4 goes to the bottom since it was on the right. So I basically rotated the thing like this is what I usually do. I go like this, 90, like that, okay? So now let's think about what's going on here. This is 1 to 2 still, right? So that actually doesn't change when you rotate it, right? But what does change is this is in the back. So this is actually S. And the idea is if you're going to manipulate a Fischer diagram and you turn it 90 degrees, you're actually drawing its enantiomer, okay? So you got to be a little bit careful when you're looking at Fischer diagrams of small molecules because this is the kind of thing that happens often. You can, it turns out, and I'll just show you one other permutation, and this is going to be a little bit weird maybe, but I'm going to rotate this, okay, another 90 degrees. So I'm going to go like this. By the way, this notation is my own notation. So I rotated it 90 degrees. Oh, I think I did my arrow the wrong way, kind of. But I'm going to rotate it again clockwise. So now I'm going to put 1 down here like this. And then 2 will be here. And then 3 will be here. And then 4 will be here. So now look what happens. Still 1 to 2 this way, right? But 4 is now in the back. So this is back to R. So it turns out you can turn a Fischer diagram. You can just flip it over on its head 180 degrees, and that's the same Fischer diagram, just turned over upside down on its head. It's for the same molecule. But if you turn it 90 degrees, then it's a different molecule. Now, one other kind of thing that you can do, and this is a little bit trickier. Not that these weren't tricky enough. But what I'm going to do is I'm going to redraw what I have up there so you can see it clearly. So this is exactly the same as what I had before. And now what I'm going to do is I'm going to rotate these groups like this. So I'm going to leave 1 in place and rotate 3. Okay. So let's see what I get. So I'm going to have 1, right? And then I'm going to have 2, and then 4, and then 3, like that. So hopefully you followed that, but the rotation, 2 goes to where 4 is, 4 goes to where 3 is, and 3 goes to where 2 is. So I'm rotating 3 of the groups, and let's assign the configuration to this one. So this is going like that now. Oops, wrong. I don't like that. I need to change that. I like the thinner blue pen. Like that. So this is R, right? And so, but this is the 4 group. This is in the back. Remember, the top and bottom are going backwards. So this is, in fact, R. So it turns out you can't rotate all 4 groups, but you notice this molecule, these are the same, right? So it is actually, this first one is R. As long as you rotate any 3 groups in the same direction, doesn't matter which 3 groups, as long as you rotate 3 groups in the same direction, you don't change its configuration. So those are some of the manipulations you do with a Fischer diagram. You'll learn, you'll use those a little bit in this chapter, but predominantly if you move on, that's what you'll be using towards the end of the second semester of organic chemistry usually. All right, so let's classify carbohydrates. Let's talk about the different classifications of carbohydrates. And in the carbohydrates, we have something called monosaccharides, and those are individual units of sugar molecules. So when you've heard the word glucose or fructose, those are monosaccharides. And the way that we classify them, the first way is by functional group. So there's this molecule, okay, and this is D-Glyceraldehyde. I'm just going to write this as CHO. So D-Glyceraldehyde, okay, and then there's this guy, and this is actually an isomer of the same molecule. Has the same chemical formula. Now you'll notice that this molecule is not chiral. This has a carbon with, the one on the left has a carbon with 4 different groups on it. This one doesn't have any carbons with 4 different groups. This is a double bond here, so that's not chiral. And these have CH2s and CH2, so those aren't chiral either. This is dihydroxyacetone. And it's the smallest of what we call the ketose sugars because it contains the ketone functional group, which makes this the aldose. Let me write it up here, aldose, because this is an aldehyde. So we have the aldehyde functional group in aldoses and the ketone functional group in ketoses. Now, we also designate by the number of carbons, okay, and the number of carbons can be designated as tri, tetra, penta, or hexa. Those the a triose, okay, is a 3-carbon sugar. So both D-glyceraldehyde and dihydroxyacetones are examples of trioses. But you can say an aldo, triose or triose, and then you can say keto, triose, to designate it's the aldehyde version or the ketone version. 4 carbons would be tetrose, and then pentose, and then hexose. So, and glucose and fructose are both hexoses. One is an aldohexose, and the other is the ketohexose. And I'll talk about that here in a second. So again, you can designate aldehyde ketone, or you can designate number of carbons, and then you can designate D or L configuration. And this has to do with the stereochemistry of the carbon that's second from the bottom, okay, in the sugar molecule. So let me draw a tetrose for you. Tetrose would be drawn like this. And I'll put the OH on the right, and I'll put H here, it doesn't matter. I'll put OH here, and this is CHO, and this is CH2OH, and the atom that's missing over here is a hydrogen. All right, so this sugar has the name D and threose. And I'll show you some mnemonics and stuff for later for memorizing all these names. And I'll talk to you a little bit about whether or not you really need to memorize them, okay? And it's kind of a 50-50 depending on what area of study you really go into. Okay, so that's D-Threose. And this is the second to the bottom carbon in my Fischer diagram. So you have to remember when I draw this, these OHs, this OH and this OH, these are pointing forward along with their corresponding hydrogens. The ones at the top and the bottom are pointing backwards. So this is D-Threose. D is what Fischer designated this as being, as to the right of the carbon in the molecule as you draw it in a Fischer diagram. And then what I'm going to do is draw its enantiomer. And if you remember to draw the enantiomer, you draw a dashed line. And then you can, or one of the ways you can draw the enantiomer, this is one of the easier ways, like this. You draw the stereocenters, when you say CH2OH, and then you just flip everything. You do the mirror image, like that. So this would be L-Threose. So this is to the left. D for like dextro, not to get confused with what we use in determining the specific rotation. We talk about D and L and plus and minus. Dextro-rotatory, we talk about that. That's not what this D and L means. It just means the left and the right-hand sides. So this is L-Threose. And the enantiomer is the mirror image at every center, but whether or not it's D or L is dependent on which side the OH group ends up on. It's either on the right, like it shows on the left, or on the left, like it shows on the right. So probably should have done those in a different order now that I think about it. Okay, so that's the D or L configuration. So you could have, for example, glucose. Glucose is a D. Oh, sorry, let me write glucose. Is a D. D-glucose, in fact, is a D-aldohexose. So there's a lot of different ways you'll hear these terms thrown around. It's all different ways of describing the molecule depending on what you're trying to talk about. Okay. Now, we do have something called polysaccharides, and polysaccharides are what make up the starches. There's polysaccharide just means many sugar molecules, and these are the monosaccharides. Okay, so it's kind of a funny thing. There's disaccharides. That would be 2 units put together. There's trisaccharides. And then there's oligo. And oligosaccharide actually includes trisaccharides, but it's anything typically from 3 to 10. I don't know why I put a hyphen in the front. There's 3 to 10 monomers put together. Or residues. Sometimes they'll talk about residues. It's the number of units of the sugar that are put together. Another way we classify them is as reducing or non-reducing. And so what this means, okay, is a reducing sugar typically reduces a metal like silver or copper into its metallic form. And the classic test is the Tollans test. That's a capital. That's the last name. And that takes silver ion in solution, in a basic solution, and converts it to silver solid. And this is actually known as the silver mirror test, or silver mirror in a test tube. I've got all kinds of names for it, but it's Tollans test. It's the way old Christmas ornaments used to be made is they would just take glass balls and they would fill them with Tollans reagent and a reducing sugar, and they were able to create a silver mirror on the inside. So anyways, that's Tollans test for reducing sugar. So it can either do that or it can't, and we'll talk about why that is in the structure later. But for now, you should know that glucose and fructose can actually both reduce Tollans reagent, even though that's people. If you look online, people will say that it's only glucose, but it's actually not quite true. It does happen with fructose, and then like table sugar, sucrose is non-reducing. Okay, the next thing I'm going to talk about is because there's a lot of drawing of structures, and I find that it's really tedious. And so many years ago, I came up with a sort of a hieroglyphic version of drawing sugars. And I don't want you to detach too much from the actual structures, but this makes the understanding of the stereochemistry and the structures, relationships to each other, a lot easier if you sort of reduce it down to its bare essentials. So that's what I'm going to do next. So I'm going to introduce this by showing you the structure for, let's say, D-Glyceraldehyde. So to start with, the structure looks like this. The top is an aldehyde, and the bottom is a CH2OH. And they're always drawn in this orientation. The highest priority functional group is at the top, and the carbon chain actually numbers downwards, so like 1, 2, 3. So that's always the way we draw them in these Fischer diagrams. So the first thing I did was I decided that I didn't need to draw the H, and so I sort of reduced it down to this. But then I still had the top and the bottom. And then I realized what I just said, those groups never change. And so then I reduced it down to this. And then I got crazy and I said, well, it's always the OH I'm showing, so now that becomes this. And really, what that does is it shows you the important aspects of the structure. We're assuming it's oriented in the sort of standard way with the aldehyde at the top and the stereochemistry of the hydroxide group is shown to the right as a D in this case, but to the right. And at the bottom, there's always a CH2OH, so that structure drawing is enough to get across the picture of what the overall structure is for the molecule. Now I'm going to show you another one. This is a ketose. And it has the ketone on the number 2 functional group, like this, and then a CH2OH, like that. So this is, if I remember right, it's erythrulose, but the D-erythrulose, and I'll get into the names in a little bit. But what I did, again, using my same sort of logic, I went through this progression. I showed where this was, and then I showed where this was, and then again, you really only have to do this. Now, because it's not hard to put the oxygen there, I usually draw the oxygen in there, and that helps to show me the overall structure. So let me put one up for you, a couple up for you actually. This will be the sugar called Manos. And by the way, I have all these memorized already, and I've never really tried to do it. It's just kind of happened over time. Now, Manos, if you're going to guess at it being an aldose or a ketose at this point, you can probably guess that it's an aldose because there's no carbons in here. And it's an aldohexose. It's actually closely related to glucose and fructose. So this is actually CHO up here, and then there's CH2OH. So what I want you to do is go ahead and draw that in its simplified form. Now I'm going to pause it, and then you can draw it. You should pause it at this point, draw it, and then when you start it, I'll have the structure drawn for you. So hopefully that's the structure you came up with. I'll draw another one that'll be a ketose sugar in this case. I'm just going to actually pause it, draw it, and then pause it again and give you time to draw the sort of the hieroglyphic version or the line version of that. So here's the structure at the top over here. Fructose, actually. Ooh, gosh, I didn't mean to zoom it like that. Just meant to move it. What I'd like you to do is, again, pause the video, draw what you think it should look like, and then compare what you get to what I get. So that would be D-fructose. Again, the OH groups are on the CH2OH at the bottom, and there's one at the top for the ketoses as well, aren't drawn, and so the OHs to the right are these two OHs, and this OH to the left is this one here, sort of like this. All right, so let's talk about. Let me show you the mnemonics for memorizing these. Oh, I noticed my screen shifted. Hang on, let me pause this for a second and fix that for you. Okay, so here are the mnemonics for remembering all the sugar structures. The first one is one that has been around for I don't know how long. The first two, actually. The top one was taught to me by a former professor at Fresno City College, and he learned it in graduate school. And so he passed it on to his students, and he actually passed it on to me. But these are for the aldotrioses to the aldopentoses, and the phrasing is get Raxel, and I don't know why people can remember Raxel so well, but they do. And so those letters stand for glyceraldehyde, erythrose, threose, ribose, arabinose, xylose, and lixose. And then the aldohexoses, this mnemonic is probably in your book, but if it's not, and this one is super common too, you can look it up, and there's others as well, but this is all altruists gladly make gum in gallon tanks, and that actually stands for allose, altros, glucose, Manos, Gulose, idose, I left one out, right here. Gallon tanks. So idose was left out of the original list. And whether or not it's DRL doesn't matter. You just have to know which way the group is pointing and all that kind of stuff at the second to last carbon. And then the ketoses, I've actually never seen one for memorizing the ketoses. I've never looked for like a standard one that people use. But I came up with this one years ago, and it's Dirk Psycho Friend Sorts Tags. Okay, so like I said, it's not maybe the best one, but it works out okay. It's Dirk Psycho Friend Sorts Tags, and so I had to think of D, that's the D, and erythrose, actually. You can get the erythrose in there as well. And then R is for ribulose, and X is for xylulose. So you notice that these are the same names as given up here, right? And we'll come back to these, why they have similar names. But they add the extra letters in there, the UL letters. So then there's psychos. Psycho, I just spelled it differently for psychos or psycho friends, right? And then fructose, sorbose, and tagalose. So those are the names. And then basically it's flashcard memorization. And once you have that, I'm going to show you how you can use these along with a systematic drawing style so that you can help you memorize all the aldoses and all the ketoses. Okay, so before I get started with drawing all the aldoses, I call it the sugar tree, and you'll see why here in a second. Before I go draw all the aldoses, let me talk a little bit about what we're going to be doing at each step. So, and then I'm going to do it not in the hieroglyphic line style, but actually just drawing it for you out. So we're going to start with the smallest. It's D-Glyceraldehyde. So the smallest would be CHO like this, and then OH and H, and then CH2OH. And what we're going to be doing when we do this is we're going to be inserting another carbon stereocenter in here. Okay. In fact, what we're actually doing is we're adding on top to this CHO group and creating another alcohol functional group. So it's actually an addition reaction. We learned about addition reactions with carbonyls. That's actually what we'll be doing. So if I do an addition reaction and I add something here, what ends up happening is I'm going to have 4 carbons in the chain. And how exactly this happens isn't actually important at this point. But we will talk about some of this chemistry later. So I can do that. And this is erythrose actually in the nomenclature, and I'll point all this out as we go along. This is CHO. So really, what I added when I did this is I added this part here, and I top it off with the CHO group at the very top. So I added an OH group and then to this carbonyl. But then here's the thing you have to remember when you add to this OH group. This is true in the chemistry of aldehydes. It's also true in the chemistry of sugars because they're just aldehydes. You're going to end up with 2. The 2 that you'll end up with, in fact, let me draw that over a little bit to the left here, are different at that 1 carbon. You get both stereochemistries at carbon number 2, and so you're going to end up with another molecule like this. And this is actually threose. This is the one I drew before. But you can generate both the R and S centers at this carbon here. And so you have the possibility of generating both, and when the reaction happens, you generate both. And so I'll have CHO at the top, and I'll have CH2OH at the bottom. And again, what I added was this group here, like that. Okay, so what does that look like when I do the line drawing style that I've taught you? I don't have a name for it. I suppose I should come up with a name. It will look like this, where when I add the top group, it's pointing towards, they're pointing towards each other like this when I draw them. So that's kind of my system, and this is how the mnemonics were generated, is for drawing all the sugars as you add the carbons on top. And I'm going to use this green like this to sort of highlight the sections that I add. But this is the way the mnemonic was developed, is by systematically drawing out all the structures so that they're always, when you add a carbon to the base, you're going to have 2 carbons pointing towards each other. Okay, so let's get at it here. We're going to do the sugar tree, and I'm going to start in the middle, and this is going to branch out quite a bit, and we're only going to do the D sugars, and then I'll talk about the L sugars here in just a second. So like I said, we're going to start with D-erythrose, and in that line drawing style that I talked about, it's going to be this, like that. Now, what I'm going to do is go right underneath that, and I'm going to draw these 2 branches out wide because I have to draw a lot of structures under here. But what I'm going to do is I'm going to go like this and like this. So those are the ones that I just drew. And the sections that I added are these, like this. Okay, so those are pointed towards each other. Now what I'm going to do is take each one of those and create a branch underneath that. So for each one of these, I'm going to take a branch like this and a branch like this. And so what I'll do is I'll draw this part's the same, right? This part is the same. And then the third one is this one. and this one like that. So that's the third stereocenter, not the third carbon, but the third stereocenter. And again, the parts that I added are these, like this. Okay. So that's the next step in the drawing of the sugars. And then again, I'm going to draw this part the same. So that part is what we got from threose, right? This part's not changed. And then this one's going to point that way, and this one's going to point that way, like they're pointed at each other. And so that creates this guy and this guy. Now there's one more layer to this, and so what I'll do is I'll draw that last layer, and then we'll sit and talk about what these structures' names are. We'll use the mnemonics devices to help us. So you can see why I spread this out so much, because there's a lot of structures. Every time you double, you get a lot of extra structures. So again, these two both look at the bottom three carbons just look like the one that's on top, right? And this one again, like this, and then this one's going to be like this, and this one's. So I'm not topping them off yet. I just want you to see how repetitious this thing gets, and I didn't quite space it out right. So, but it's going to be close enough, I think. So then I have this, and then this. Right? Those two are the same, and these ones are both going to be like this shape. And now what I can do is I can add the bits that I put on the top, the next carbon in, like these guys here. And again, these guys will be pointing towards each other like this. And it's just a pattern that was used to generate all the sugars. In fact, synthetically, if you were starting with D-erythrose and building all the sugars from D-erythrose or D-Glyceraldehyde, you would actually have to follow the same process to get to each sugar. Okay, so then the bits I added, I'll highlight in green again. They're pointed towards each other all the time, like this. This is the same pattern we'll do for the ketoses as well, so try to keep that in mind. And so what about the mnemonics? So I'm going to write the names in, and then we'll come back and you'll take a look at it. But maybe you could pause it. And this is for the aldotriose to pentose, right? That's this part. This is the get Raxel part. And this is the all altruist gladly make gums in gallon tanks. That's the aldohexoses. That's here. In fact, let me do this. Just draw it in like this. Color code this a little bit. Sorry, it's not exactly straight, but it's. I think you get the idea. So I'm going to fill in the names, but you can go ahead and fill in the names as well. These are all the D sugars. So this is actually D sugar tree. I know that's kind of corny. The L sugar tree would be the mirror image of every structure. Okay, and we'll talk about that again, like I said, in a bit. And we're going to pause and fill in all the names. So here they are. I wrote them. They're kind of small, but I think you can read them when you zoom in on the notes. There's get, the glyceraldehyde, erythrose, and threose. Raxel, ribose, arabinose, xylose, and lixose. And then there's the all altruist gladly make gum in gallon tanks. And you'll see why the GU is important in this, because that's Gulose, gum, and then GA. So that helps you keep them from getting mixed up. And gladly for glucose, and Manos is make, right? So all altruists. So if you'll notice, for allose, all the OH groups are pointed in the same direction. That's how it gets its name. And then altrose is only different at carbon number 2. So if you remember, this is 1 and 2 and 3 and so forth, all the way down right? 4, let's say 5, and then 6 all the way. So they're different at C2. So these are known as C2 epimers. So epimer is a term used for stereoisomers with many stereocenters, basically, where they differ at one configuration. Okay, so they're the same all except for one, and so that's what the term we use as epimers. And so if you look at Gulose is a C4 because this is 1, 2, 3, 4. It's a C4 epimer of allose, and then Talose is not considered to be an epimer because it has 3 of them that are different. So epimers are generally considered different only at one carbon. You will hear it referred to occasionally when they say, oh, it's epimeric or it's epimers, and they'll list a couple of carbons. That's not really quite the right use of the term as far as I was taught. Anyways, we can do the same thing for the ketoses, and so I'll start you out. Sorry, there's a little wind blowing. My computer gets so hot I have to blow a fan over it. So the ketoses, I'm trying not to have it blow close enough to the mic. The ketoses start with dihydroxyacetone. And then you insert the next one at this point here. Okay, so when you draw these, you're going to have a branch that goes out like this again, and a branch that goes out like this again. You're going to draw this, and you'll draw this. Now, dihydroxyacetone doesn't have any stereocenters in it, but when you add that OH group between the ketone group and the last CH2OH at the end, that becomes a chiral center. So that's your first stereocenter. And then you'll notice that this is D and this is L. That first designation, this group here, right, that's telling you it's D or L, and then from that we draw all the other ketoses. Okay, so we're going to branch out like this. Now, you recognize that this is a tetrose already. This will be a pentose, and then we'll have hexose down here. Okay, so what I'll probably do is I'm going to shift all this stuff over like this. So I have a little bit more room to draw, and then we'll draw them all. Okay, so go ahead and try drawing them out and see what you get. I'm going to also move this hexose out of the way because I'm just trying to give you a little idea, and then we'll put the names to it. So here are the structures. I drew them all out and named them. I want to point out I did make a mistake. I didn't read my own notes correctly. This is tagatose, not tagalose. And then there's sorbose and fructose and psychose at the bottom. So let's start at the top. Dihydroxyacetone, erythrulose, ribulose, xylulose. And if you look at ribulose, right, look at the structure where they're all going to the right like that. And then come back up here and you look at ribose. You notice ribose and ribulose, they're only differing in this position here, where ribulose has a double bonded oxygen. It's the ketose, right, here. So the bottom two are the same. Xylulose, they're opposite directions at the bottom. And when you look at xylose, it's opposite at the bottom. So this represents the structure of ribulose as an aldose, with everything to the right, and this is xylulose as an aldose. Right. Okay, so anyways. So these are the structures. Now, do you have to memorize these? I'm not going to say that in this class you have to memorize them necessarily. It really depends on where you go in the future. I generally have students memorize it because it's not hard. It's systematic. It requires a little work. I've had students tell me when they go on to biochemistry courses at other universities that they've had to have these things memorized. This along with the amino acids on their first day of their biochemistry class. They just took a quiz on it. And so that's not an unusual occurrence. You're expected in a lot of universities to have learned these structures in organic chemistry. It's one of the last things you do so that when you take a biochemistry class, or if you are going on to a biochemistry class, you'll know all these structures. So I'll leave that up to you. You can, of course, on an online course, have these things all outlined. You should outline them for yourself and draw notes for yourself and reference and put notes to different structures so that you'll know what the different structures are and have those things at hand for quick reference. All right, so now notice how many aldohexoses there are, right? And then if you look at the ketohexoses, there's only half as many. And the reason for that is simply this. Let me write something here, and this will look familiar to you when I write it. 2 to the n is equal to the number of stereoisomers. That's the maximum number. So for the ketoses, there's only 3 stereocenters. So 2 to the 3. So that's 2, 4, 8. That's 8. There's 8 stereoisomers. Now I've drawn 4 here, but you have to remember these are the D ketoses, ketohexoses, hexoketoses, sorry. And then it could be said either way, I guess. I'm not thinking too hard about it. But for the other half, those are all the L's. So that's why you see only 4 here rather than 8. And the reason you have more of the aldoses is because there's another stereocenter. So if you take 2 to the n, right, that's going to be 2 to the 4th. That's equal to 16. So there's actually 16 aldohexoses, but these all represent the D's. And if you draw the mirror images of all these, for example, instead of D-allose, you draw L-allose, that will constitute another stereoisomer. That's where the other ones are. They're not actually drawn because I started with this stereoisomer and said, hey, that one is going to the right-hand side. And since it's going to the right-hand side, I've essentially eliminated half of the stereoisomers, the L isomers, in these drawings. So we'll talk next a little bit about the chemistry of sugars. So one of the reactions you learned about is hydride reduction, sodium borohydride, lithium aluminum hydride. And just to remind you what those reactions look like, if you take an aldehyde or a ketone and you react it with sodium borohydride, so normally this is written something like this, 1NaBH4 and 2, it's usually water, or sometimes it's hydrochloric acid, it's an acid. What you'll end up with is you'll add a hydrogen there and a hydrogen there, and you'll end up with an alcohol. So if it's an aldehyde, it'll be a primary alcohol. Ketones will give you secondary alcohols. Sort of like, aldehyde, ketone. Same arrow. You'll end up with that being converted into an alcohol. So that is a hydride reduction. It's a very common reaction in organic chemistry to do that, to get primary or secondary alcohols. Now, when you take a sugar and do that, so now we're going to do glucose, right? So glucose looks like this. And then I have CHO at the top and CH2OH. This is an aldehyde, so what I'll get at the top here is I'll transform that into an alcohol group. And so that'll look like this. So this is what we, CH2OH at the top. So I've reduced the aldehyde to an alcohol. This is what we refer to as glucitol. Now, there are a lot of ways to get glucitol. We'll talk about that a little bit. I don't expect you to remember all these sort of permutations, but the idea of a sugar alcohol is sugar alcohols are sweet. So it turns, and they have the same sweetness because they have roughly the same shape as like sugar molecules. When you taste them, they activate the same kind of receptors, and they give you that same sweet sort of taste sensation. Interestingly, though, for many of these sugar alcohols, the ones I know about, like sorbitol and things like that, those actually don't have any caloric value, so you can eat them, but then they don't have that sort of calorie effect that you would get from eating glucose or sucrose, which is glucose and fructose as a disaccharide. Okay, so it turns out you can also get glucitol from L-sorbose, and so I'll show you that next. Okay, so to get the structure of sorbose, this is how I actually recommend you use these drawings. You just go up to here and you see, oh, there's sorbose right there, right? And then I'll redraw that. And I'll talk a little bit like what kind of test questions you might expect to get. But it would look, D sorbose looks like this. So this is D sorbose. L sorbose, again, just to practice, you do the mirror image. I'm not going to flip the ketone part because that part doesn't change. And that would be L-sorbose. Okay. Now, if I do a reduction of L-sorbose with sodium borohydride or lithium aluminum hydride, there's actually other ways to do this, right? But I'm just going to say R. Then you'll convert this functional group into an alcohol. But when you do that, you get both both stereoisomers out. So that's going to become both this. Sorry. And this. Old habits. Now, take a look at this structure, right? And remember we talked about manipulating Fischer diagrams. If I flip this around 180 degrees, and you know you can do that because we played with that at the beginning of the lecture, then what will happen is you'll have actually this structure. Everything on the left will be on the right, and everything on the right will be on the left, and you'll flip the order, right? So you're going to have this, 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 and this. And this structure, right, is the same as that structure. So at the top and the bottom, I have CH2OH, right? I didn't draw them, but you have those groups. So what you get is you get glucitol from L-sorbose. And this is actually what you probably have heard of as called sorbitol. And sorbitol is an artificial sweetener that people use. Funny side story, sorbitol is also a laxative. And so there was once a story, it was actually published a few years ago in a medical journal, of a lady who had diarrhea for many years, actually, or many months. And in order to alleviate her nausea, she started chewing more gum, and that led to more diarrhea. And so they eventually diagnosed her as having just eaten too much sorbose all the time through chewing. I don't know how much gum she must have chewed, but she must have chewed a lot of gum to make that happen. If you go look up the numbers, it doesn't take that much, but you would have to chew a lot of packs of gum to get it. Anyways, yeah, so glucitol, sorbitol, those are actually the same compounds. Both are used as artificial sweeteners, and they just get their name based on what they're derived from. So I want to show you one more example. Ooh, I zoomed again too far. One more example, and I'll start it, and I'd like you to draw the sugar alcohols sort of as a practice example. So we're going to start with fructose. Okay, well, I'll draw fructose for you. Remember, fructose and glucose look the same, except it has one less stereocenter that's occupied by a carbonyl group. And so now you can draw glucitol and mannitol, and I'd like you to identify those. So this is D-fructose. And then I'm going to pause, and I'm going to draw it, and then you try and see what you get. So these are the structures that you get from the reduction of fructose, reduction of fructose, and one of these is glucitol, and one of these is mannitol. So this one is mannitol, and this is glucitol. Right? And if you look back at glucitol, right, you can see the structure is the same over here. So those two structures are the same. So there's a lot of ways to get at these different sugars by reduction reactions. Now, briefly, there's a couple of oxidation reactions. There's a mild oxidation using bromine, or you can use silver oxide and NH3, which is Tollans reagent. We talked about that before. And when you do the mild oxidation, you get the aldonic acid. So if I take glucose and I oxidize it, that's fructose. What happens when you make the aldonic acid is the aldehyde functional group becomes the carboxylic acid functional group. So that's going to become this. And I'm going to draw out the structure just to remind you what it is. So this is known as an aldonic acid. This one in particular because it comes from glucose. This is D-glucose. This is D-gluconic acid. Okay, it's a carboxylic acid form of the sugar. And one way to remember that it's aldonic acid is to look at the name and the ON, because one end is oxidized. So aldonic acid. This is something I picked up from Bruce, actually. One end, the on end, is oxidized. Now, if you do the same reaction with a stronger oxidizing agent, this nitric acid, oh gosh, what you actually end up with, and so this is with HNO3, you end up with an alderic acid, and so the top becomes a carboxylic acid, and the bottom becomes a carboxylic acid, but the middle carbons retain their original stereochemistry. So this is known as glucaric acid because it comes from glucose. Oh, acid. Gosh. Now, and the way you can remember that is both ends are oxidized. So what I'll be talking about next is reactions to make sugars longer, more carbons, or shorter, so fewer carbons. I'm actually skipping this little section that's up here. That's actually for the other class. And I'm basically using the same notes and sort of simplifying what I say a little bit. But most of it actually is exactly the same. But I thought I'd re-record it so I didn't have the confusion of the stuff that you're supposed to know for Chem 28 and the stuff you're supposed to know from 8. So I'm just basically covering what's in your book using the same notes. So the cyanohydrin reaction, this is supposed to be reaction. And this is review because it's actually used in this Killiani-Fischer synthesis that's down here. But the cyanohydrin reaction is basically this. You take an aldehyde and you use HCN and then CN minus in catalytic amounts, so small amount. So what they say catalytic means there's just a little bit, so a small amount of cyanide present, and this acts as the nucleophile, and what you end up with, without showing the mechanism, what you end up with is this. And it's a nucleophilic addition reaction on a carbonyl group. And you can do the same reaction at ketones as well, but it's more prevalent at aldehydes because aldehydes tend to be a little bit more reactive because they're less sterically hindered in their intermediate. And that's all stuff that we sort of mentioned before. So this is a cyanohydrin reaction. Again, not worrying about the mechanism, but we're making adding a cyanide to a carbonyl functional group and also converting that to an alcohol. So in the Killiani-Fischer synthesis, this is for making, we'll call it a chain elongation reaction, which basically means you're adding carbons to it. And the basic steps in the reaction, and I'll start with D-Glyceraldehyde. And I'm actually going to draw most of this out here, including the carbon in the middle. I mean the carbon at the top. So it looks like this, and then I have this carbon, and then I have an OH, and then I have an H over here, and I have a CH2 and an OH. And in the elongation reaction, the first step is to use cyanide, so HCN. So it's the cyanohydrin reaction with a little bit of CN minus, like maybe sodium cyanide or something. So I'll just say CN minus. And the second step is a reduction reaction followed by hydrolysis. And so the reduction reaction uses hydrogen with the palladium catalyst that's been poisoned, is what they say. And that makes it less reactive. So what ends up happening after this step is you get this compound. So the bottom structure doesn't change. I still have the OH to the right. And then what I'm going to do is I'm going to add a new OH group. And because of the stereochemistry of these addition reactions, I'm going to have one group that points this way, and then I'll have its enantiomer as well. So you realize I have this OH here, or not its enantiomer, but its epimer, sorry, where the OH goes like this. And at the top I have the C, and it's going to be double bonded to the N, and an H like this, and an H like that. So I have that at the end of both. And so this is a partial reduction of the cyanide functional group. Remember, the cyanide molecule looks like that. And so what I'm doing is I'm getting rid of one of the double bonds. And it turns out when you put this in water, what it'll do is hydrolyze back to a carbonyl functional group. So these will hydrolyze into, and this will be the shorthand notation. All right. The tetrose, which looks like this and like this. And again, at the top, I'll have a CH and O. And to do this, I just do H plus and H2O. And the water removes this nitrogen. It actually releases ammonia as a product. But you end up just adding a carbon, and one's going in one direction and one's going the other. So these are epimers of each other. Okay, so back to review what we're doing. Here I had a triose or triose, right? Aldotriose. Now I have an aldotetrose. And I've generated both erythrose and threose. And if you remember when we were learning how to draw these, right? that's how we went about drawing the structures. We started with D-Glyceraldehyde, and I add one carbon at the top and another carbon at the top of that, and I get erythros and threose. Now, if you separate these two, these are diastereomers, and they have sufficiently different properties that you can separate them and run the same reaction. I can take erythros and create ribose and arabinose, and threose can be converted into xylose and lixose. And so the way I showed you how to draw it is actually the way when the sources weren't available, that you could create each of the sugars of the aldoses. Okay, going back. The last thing to talk about is the rough degradation reaction, and this is the opposite process, not chemically opposite, but structurally opposite process, where you take, let's say, a hexose and create a pentose out of it. So, for example, in the rough degradation reaction, I can, highlighter. I can go like this. So I'm going to draw, again, I like to stick with glucose. It helps you remember. It's one of the more important ones is a CHO. This. You would do the rough degradation, and what you'll end up with is this. Oops, sorry, and I chopped one off the top so that doesn't have to be quite so long in CHO here. So literally you're just taking this top carbon, chopping it off, and converting this into the aldehyde. So that's what you end up with there, if you can see that in the structure, right? Because this part is the same. And you've only gotten rid of the top carbon, that's this carbon, this is the one that's missing, and then converted this second carbon into the aldehyde functional group. So in the rough degradation, it's actually a couple of steps in the reaction. One would be, keep doing that. One would be Br2 and water. And if you remember, that's one of the mild oxidation methods. So what it does is it converts the aldehyde into carboxylic acid. And the second step is what's called a decarboxylation reaction. And you don't need to know this reaction, but this is what it is. There's a catalyst, an iron sulfate. Or it's not a catalyst, it's a reagent, which helps to do the decarboxylation reaction. So that essentially goes through this process. The first steps is 1. This converts this into COOH, and then all the other groups are still there. And then the last step is to convert it into that, but at the same time it removes CO2. And so you can create a 1 carbon shorter version of a sugar out of, for example, glucose or fructose or arabinose. All those can be converted into shorter carbon chained sugars. All right, so again, you don't need to know that reaction, but that's one that's pretty well discussed in a lot of different places, and so I felt you should know it. It's not actually in your book, okay? So then, at least I don't think it is. The last thing one of the last things I want to do before talking about polysaccharides is how to sort of describe how Fischer determined the structure of glucose. And basically I was going to describe like what he knew and then what experimental evidence he gathered and how he used that to determine the structure. Okay, so I need to talk about, there's another very important aspect about sugars that needs to be talked about, and that is their cyclic forms. Now, what we've been drawing is known as the open chain form. So I'm going to do this for glucose, and glucose looks like this in its open chain form. And on the top, I kind of drew that a little out of perspective, but that looks like that. That's the open chain form. Now, it turns out that when you put glucose in water, it's far more stable in a cyclic structure. It's called the ring form or closed form or closed chain form. But that actually looks like this. And I'm going to teach you a new drawing style. It's called a Haworth drawing or diagram. And it's what you see in most biology textbooks. If you've been looking at glucose this whole time and saying, that doesn't look like glucose, that's because we learn it like that, usually in biology. And there's a couple of things about this structure, and I'll explain to you how you go from one to the other, but it looks like this. And then I should point out that these OHs, right? And that's not an OH, that's a CH2, and then an OH like that. Okay. These all have corresponding parts in the open chain form. Now there's one thing that I'll have to show you, and I actually haven't drawn this carbon in yet, so I'm going to highlight it yellow. Okay. Well, maybe I'll do green. Green might show up better. Yeah, that shows up a little better. That's actually this carbon here. So that in terms of numbering, right, that's carbon number 1. Then this is 2 and 3 and 4 and 5 and 6. Okay, so this is what I'm going to do. I'm going to start with number 1 here. Okay, and you notice I didn't draw the oxygen on it because I'm going to draw that out in a second. There's 2 forms of this that I'll draw out for you. And so this is 1, 2, 3, 4, 5, and 6. And the oxygen, okay, is the oxygen actually on carbon number 5. And so I'm going to draw that like this. And that's this oxygen here. So, oh, sorry, and I didn't finish writing what I was supposed to write, CH2OH, like that. So how does this happen, right? Well, you remember, this is an OH group down here, this red guy. What he does is he comes back around and does a nucleophilic addition reaction to that carbon. Now, when we talked about ketones and aldehydes, we talked about hemiacetals and acetals. And what this is going to be is it's going to form a hemiacetal. Let's see, just do this real quick. If you have an aldehyde like this, and you react, or ketone, doesn't matter, but we're dealing with aldehydes here, so I'm dealing with aldehydes. And you add an alcohol to it, and you do this under acid catalyst, what you'll end up with is the carbon, an alcohol. So these are the same guys here, those carbons. I have the OR group, and I have the H, like that. And this is known as a hemiacetal, and you can recognize it because there's an the link looks like this. It's O C O C, like that. And this is an OH, right? So that's a hemiacetal. If you continue this reaction and provide a little bit of heat and do a little distillation, you can form the acetal out of it, and the acetal looks like this. And this takes 2 molecules of the alcohol, and then that water comes off during a distillation, usually like that. And then this is plus H2O over here. But this is 2, I guess the simplest way to think about it is 2 ether connections on the same carbon, okay? This top one is an alcohol and an ether connection. So that's a acetal, hemiacetal, and this is the acetal. So this is what the sugar's doing, okay? So what happens at this carbon here is you have an alcohol functional group. And it can either be going in the upward direction or it can be going in the downward direction. And so the way I've drawn this is known as beta. And then 6-membered rings are known as pyranoses. So it's beta glucopyranose, because it comes from glucose, and it's actually beta D-glucopyranose because this is the D form of the sugar. Now, there's also an alpha glucopyranose, and in the alpha glucopyranose, the structure looks like this. So these OHs don't change. They're invariant in the structure, that is for glucopyranose. there's a CH2 and an OH like this. Okay. Then on this one, the alpha is pointed downwards like this. And this is alpha glucopyranose for the D-glucose. And the things that I want you to notice is you're going to have to be able to draw these on a test or recognize them on a test. Is how you go from the open chain form to this closed chain cyclic structure, the glucopyranose. And we're not going to do the glucofuranose. So that's, again, stuff for the other class. So in a glucopyranose, the way you recognize it is you notice if it's on the right, that's carbon number 2. On carbon number 2, it's down. If it's on the left, it's up. And if it's on the right, like carbon number 4, it's down. So I usually write this out. R-A-D, like rad, right? So if it's right, it's down. And it's also to help you remember the A is for the alpha. The alpha form has the alcohol pointed in the downward direction. So why is that an alcohol, right? It's an alcohol because when the alcohol attacks the ketone and this opens up, eventually that will form an alcohol. And so that alcohol is from the original, right? This OH is, do it in yellow. This OH, that oxygen is this oxygen here, okay? So write alpha down will help you remember how to draw these structures. So let's say I do a different sugar, and we don't even have to give it a name. Let's say we do this. And this is an aldose. This is CH2OH. What I want you to do is draw the pyranose form of that. And so I'll pause it, and then you can check out to see how I did it. So this is idose. And you would write the name as pyranose. I had to think about it. Yeah, like that, idopyranose. And now I didn't draw an alpha or a beta, so what I'm going to do is I'll draw this in the downward position just because I think it's cool that way. But this is the downward position like this, and I'm going to make OH. So this is to the downward direction, so this is alpha idopyranose. There's also a beta form where that goes up. So let's see how we did this. I numbered my carbon chain 1 through 6. I numbered the carbons in the ring 1 through 6, not the oxygen, but the ring, right? The carbons, I mean. And then I looked to see which direction each group was going, right, relative to the open chain form. And then if it's to the left, I made it go up. And if it's to the right, I made it go down. So you can see how at carbon number 2, it's to the left, it's up, to the right, it's down. Now, there's a cute little trick. It's a little bit of a mind bender, but it's a cute little trick, is if you just take this structure and you turn it on its side, right? So I just take this structure and I'm just going to write it sideways now. So I drop it from being this way, and I tilt it down like this, then it's going to look like this. Again, this is a little bit of a mind bender. But if you'll notice, this is 2, 3, and 4. That's the same as the 2, 3, and 4 over there. So you think of like taking this open chain form and laying it on its side. We're not doing any stereochemistry or anything like that on this, and we're just laying it over. That's what it's going to look like. So another important form to know is Fructose Furanose. Now furanose is a 5-membered ring. We normally draw it like this, and if you've had biology classes before, you've probably recognized this shape. But it looks like furan, which is an organic compound that comes actually originally from the heating of fructose. but a fructofuranose is the 5-membered ring that fructose makes when it forms its closed chain form. So if I draw fructose, it's going to look like this. Again, remember, fructose is easy to remember because the bottom 3 carbons are the same as glucose, and then I have an oxygen that looks like that. So there's an oxygen that's down here. Now I'm going to draw that one in. I don't normally draw that in, but that's this oxygen that's here. Now, the carbon that it attacks is it attacks that one. That's that carbon there. So you notice the thing that's going to have on it that's different than like a glucopyranose, for example, is that it's going to have a CH2 group on it, as well as the alcohol group, like that. So this would be the alpha form, because it's pointed in the downward direction. So we're going to call this carbon number 1. It's not really carbon number 1, but it's easier from the purposes of drawing the ring to call that 1. This will be 2 that's here. This will be 3, 4, and this will be 5. Now, there's really 6 because there's 1 that's up here. And then this oxygen is this oxygen in the ring. So, like in glucose, this lowermost carbon is going to be CH2OH, like this, pointed in the upward direction. Now, this is 1, 2, 3, 4, and this is 5. Now, the initial CH2OH, that's this guy over here. Again, that's the one that's coming off on this end here, like that, okay? That's where that one's coming off. That's the CH2OH there. Now, if I look at 2 and 3 and follow the sort of the directions that I gave before, 2 would be in the upward direction and 3 would be in the downward direction. So there's an OH, and this is carbon number 2 in the ring, and then this is carbon number 3, and this is the OH going down like that. So that's fructofuranose. In its alpha form. In the beta form, the OH and the CH2OH switch sides. One goes up and the other one goes down. Okay. Now, you can form with the cyclic sugars, you can form what are known as glycosides. And these are acetals that are formed from the hemiacetal. So let me draw a glucopyranose for you again. And we'll do the alpha form like this. And then you can imagine the rest of the stuff filled out. This is, the CH2OH. But I don't want to detract from what I'm trying to show you here. So the rest of this is glucose. It could actually be any of the other sugars. And then what happens is if I react this with 1 mole of alcohol under acidic conditions, with an acid catalyst, in other words, what I can get to form is this. Okay, so what's happened is you've done a substitution reaction of the alcohol with the OH functional, the alcohol functional group, with the alcohol that you put it with. And this is known as a glycosidic bond. And there's both, again, there's alpha and beta glycosidic bonds. This would be the alpha form because it's pointed in the direction, of the downward direction. So this is known as the glycosidic. Now, it's spelled S-I-D-E, right? Glycosidic. Instead of C-I-D-E is like the poison suffix, so glycosidic bond. Oh, I meant to say glycoside. It's a glycoside, but it's glycosidic bond. There we go. All right. Yeah, so that's all I really want to talk about. We're going to skip this section. This, again, is stuff for the other class, so we're going to pass on that. I want to talk about some disaccharides. So when you form disaccharides, actually what you're doing is you're forming glycosidic bonds between 2 sugars. So I'm going to take 2 sugar molecules, 2 glucose molecules actually, and draw what they look like in the molecule maltose. And I'll fill out the whole thing. And so what I'll do is I'll draw it. You should pause the video and try drawing it yourself, and we'll draw the alpha form of the disaccharide that we're drawing. So see if you can do that. So they're both glucose, 2 molecules of glucose connected like I've shown you in the middle there. And then what you have to do is decide what the alpha form looks like. Okay, so that's what it looks like, and just to remind you, this is what glucose looks like, and so when you lay it down, number 2 will be down, number 3 will be up, number 4 will be down, and so this is 2 glucose molecules in an alpha 1,4' glycosidic bond. Okay, this is the reason it's called 1,4 is because this is the number 1. Okay, and this is 1, 2, 3, 4. So it's known as a 1,4' because that 4, it's not connecting to the 4 on its own ring, but it's connecting to the 4 of one ring to the 1 of the other. Now you'll notice on carbon number 4, this one's pointing down. It's pointing down because in glucose it has to point down. So this is glucose, right? This is glucose connected in an alpha 1,4 glycosidic bond. The alpha form for maltose, so this is what makes maltose. But there's both alpha maltose and there's beta maltose. Like malted beverages, that sweet malted flavor. Anyways, that's what it is. There we go. That's the alpha form because it's pointed in the downward direction. The beta form, that points in the upward direction. Okay, so maltose is an important disaccharide in the sense that it's closely related to starch. Okay, and what you'll see in starch is 2 different polysaccharides. The simplest form, which is called amylose, and I'll talk about this more later, is just 1,4 connections, and then amylopectin, sorry, I had to think about what the word was, are connected 1,4 and in the 1,6. Okay, so I'll show you what some of those things look like here in a little bit. So this is the digestible form. It turns out the alpha 1,4 glycosidic bond is the bond that we can break in our own biochemistries and use the sugar molecules that come from it as a source of energy. Now, cellulose is paper fiber, is what we normally think of as paper fiber, is also a polymer of glucose. The simplest form of it, the disaccharide form, is known as cell biose. And cell biose is connected by a beta 1,4' glycosidic bond. And again, it can be in either the alpha or the beta form. So this is what I'm going to do. I'm going to pause it, and then you try to draw the beta 1,4' glycosidic bond between 2 glucose molecules. And I'll remind you that the linkage on the monosaccharide that will be on the left side of the drawing will be in the beta form, so it'll be in the upward form. So let me draw that while I pause this video, and then when you restart it, see if you got the same thing that I got. So this is what you should have gotten for cell biose. It's a beta 1,4 glycosidic bond. I drew the beta form of it. I maybe should have done the alpha one again. But this is beta here, and this is carbon number 4. Remember, carbon number 4, the OH goes down, so I had to draw this up so that I could draw it sort of in a straight line. And then this is drawn, this is beta, right? And this is beta. So this is beta cell biose. In alpha cell biose, you'd still have the beta 1,4 glycosidic bond, but the terminal OH group. That one on the far right would be pointed in the downward direction. Now, in cellulose, what you have is you have not just a disaccharide, so we're talking about disaccharide. You'd have a polysaccharide, and this bonding pattern would repeat over and over and over and over again. The last important disaccharide is sucrose, which is table sugar, which is a disaccharide between glucose and fructose. I think the easiest way to draw it is actually like this, and it's a little weird. They usually draw this bond really long, maybe not quite that long, but put the oxygen in the middle. And it turns out they're both connected to each other by the carbon that was originally the carbonyl functional groups on each. Okay. And then we'll talk a little bit about, so that's what it would look like. So for fructose, this would go like this, and then for glucose, it would be like this. And then this would be CH2OH, and this would be CH2OH. So this one is beta, and this one is alpha. And they're connected through what is known as their anomeric carbon. This is the anomeric carbon. I think I forgot to say that. So let me go back up and just talk about this for just a second. So when I draw this, this could be in the up or down position. Because it can be up or down, they're referred to as anomers. Okay, same thing for glucose. If I just go to the monomers, this would be the alpha. This would be an alpha version, and the up version would be the beta version. Okay, so alpha and beta anomers is a term that we use, but they're connected through their anomeric carbons in table sugar. One of the things that this causes to happen is, remember, this oxygen on each would originally have been the carbonyl, so that bond doesn't as readily break because it's hard for this. You need to get another oxygen in here and break this bond. Because they both want to turn that same oxygen into the carbonyl functional group. And so because this can't open up into its aldehyde form, like this can open, this one can open back up to the aldehyde to become the straight chain form or open chain form. This can't be reduced. So table sugar is known as a non-reducing sugar, because it can't reopen up the anomeric carbon and create the carbonyl functional group out of it, which then can be used as the reducing sugar. I've already talked about that, so I'll pass on that. And then I want to quickly talk about polysaccharides, and then I'll mention a little bit about sugars in DNA and RNA, and we'll start with RNA, but let's go ahead and do polysaccharides first. So the term you guys are probably most familiar with is starch. And starch is actually made up of two components, 80% of it, roughly. It depends on like the source of the starch, I think, but 80% is amylose. And the other 20% is something called amylopectin. Okay, so let me, before I do this, I have shorthand notations for stuff. And so when I say alpha 1,4 glycosidic bond, I usually just draw it like that. Rather than draw the rings, because we're going to be drawing lots of these. Let me go back up to here real quick. All right. So this is an alpha 4 1,4 glycosidic bond, and I would just draw that like this and that. Okay, so this bridge, I don't try to show what it looks like. I just assume that it's going to be alpha in these sugars or beta, depending on which sugars we're talking about. But for amylose, it's all alpha 1,4 prime. Okay, so now polysaccharides can be drawn like this, and this is 1,4 prime glycosidic, and in this case it's alpha. Okay. For cellulose, it would just be beta, and the equivalent for amylose would just be the same structure like this over and over and over again. That's what amylose is. It's just a long polymer. It's a polysaccharide of sugars, glucose molecules, in an alpha-1,4 glycosidic bond pattern here. Now, amylopectin does something a little bit different. Okay, so this is what I want to show you. If I have a glucose that looks like this, remember I said you can connect 1 to 6. So it is possible to connect this to another, this is 6, another sugar like this. Okay? So if I can connect it to another sugar like that, that's an alpha, because this is down, 1,6 glycosidic bond. So in amylopectin, the way I would show that is you have 1,4 bonds that go like this, and then you have branching like this. And so this represents that linkage that's over here. It comes up to a carbon and branches off. And so what will happen is you'll have a whole bunch of these residues like this. That's what they're called, the sugar molecules. And then every, let's say 20 or so, books vary on what they say, you'll have another branch like this. And then, you know, I'm showing just this one chain, but this would be like approximately 20 sugar residues. There'll be a branch that comes off, and then every 20 or so residues, there's a branch that comes off of there. So if I'm drawing, this is not this is amylopectin. Sorry, I shouldn't have done that. If I draw it from the bottom, and this is the way I like to think of it. If I take and draw this, and I have a long chain of it going like this, every 20 residues or so, it branches. So it might go like that. Let's say this is 20, and it branches like that. Then go another 20. It's not quite this regular, but it's something like that. Then even these branch and then continue on, and then branch and continue on. And so this is kind of what it's going to look like. This is these long tangle of ends. And I kind of in my head imagine it looks like this. And if you think about the branching happening over and over and over again, from one starting point you get many, many branches coming off. So it kind of looks like a tree with a really thin trunk, right? But it's like a tree. And then these are all the ends. And the importance of the ends is that's the part that hydrolyzes when the organism that creates the starch needs the sugar molecules for energy. So amylopectin has branching about every 20 or so sugar residues, and so the branching is far in between each branch. Okay, so that you have a branch that comes off, you go about 20 more carbons, you get another branch that comes off, you go 20 more carbons, you get another branch that comes off, and so they're pretty spaced out. This is what you find, starch is what you find in plants. In animals, instead, you find glycogen. And glycogen, the only real difference is the frequency at which it branches. And I've seen anywhere from like 4 to 10 residues. It's not an exact number. It branches. There are alpha 1,6 prime branches on a normally alpha 1,4 sort of chain. There's a 1,6 branch about every 4 to 10 residues. That is exponentially more ends on the tree. So rather than looking like this tree that's up here, it's going to look more like a bush with lots of little pokey ends coming out of the end. And I just sort of liken it to this. If you're an animal and somebody is coming to eat you, you will need energy right away, and you will run, and then you'll use that energy sort of to replace the energy you need, but also to create the energy that you need. And then in plants, well, like if you're a potato, you don't usually run So you don't need to have that rapid sort of source of energy. So the branching is less. There are fewer ends. But in times of when you need it to produce more buds or whatever, you can access it still in a plant. Okay, but the only difference between plants and animals in this respect is just the degree of branching that takes place. So glycogen is what we have in animals, and then starch is what we get out of plants, and that's a combination of amylose and amylopectin. And glycogen and amylopectin are very closely related to each other, just differing in the degree of the branching. Okay, so before I talk about what DNA is, I want to actually talk about RNA. And this stands for ribonucleic acids. Now, if you remember what ribose looks like, it looks like this. Hang on. Sorry, I got wind blowing in my microphone. Anyways, we'll just live with it. It looks like ribose, and we'll do D-ribose. Looks like this. And it forms a pyranose, a 5-membered ring, and the first carbon, of course, will be this one. Then 1, 2, 3, 4, and this is 5. So, or this is the 5th carbon, but this oxygen is the one that's in the ring. So I can draw a 5-membered ring. Give myself a little bit of space here. And then we can draw either alpha or beta. I'll just make this one go up, so this would be beta. And then this oxygen is this oxygen here. So what I've done, actually, let me draw this actually in blue, and then I'll just use the highlighter on it. That's this guy here. And then 2 and 3 are both pointed downward. So this is 2, 3. And then 4, right? 2, 3, 4 has a CH2OH that goes like this. And this is the pyranose form, ribose, and that's the ribo in the ribonucleic acid. Now, I'm not going to spend a lot of time with talking about what the different bases are, but the basic structure of RNA looks like this. The bases, which you may or may not know, it just depends on how much biology you've had, or if you've had any at all. The bases are the adenine, guanine, thymine, and uracil, I think. A, T, G, C, or U. Yeah, for uracil, for RNA. This is what the bases are connected to. It's a ribose backbone, okay, a ribopyranose, and then I have CH2. This will go to an oxygen. Now, in RNA, when you start putting the bases together, they're connected by what's called a Phosphodiester Bridge. And I didn't leave myself enough room, so I'll space this thing out. Hang on. Almost out of page space here, so I'm trying to be a little conservative. May move stuff around in a second. So it's connected to the C3 of another ribopyranose, and so it would look something like this. Again, I have an OH right now here, but that's where the base would be connected. And then this would be CH2, then an O, and then on to another base. And then I have an OH group here, just like I did in the other structure, except for this one, it didn't come. I started here, so I didn't have another thing attached, the phosphate attached here. Now this is called a Phosphodiester Bridge, simply because when you think about an ester, it's like a carbon, oxygen, carbon, but in a phosphate ester, and the carbon is a double bond on it. In a phosphate ester, you have a carbon, oxygen, phosphorus double bonded to oxygen. And then it can have an ester on both sides. So that's why it's an ester bond on this direction, an ester bond. So we give it the name diester. Okay, so anyways, in ways that's neither here nor there. And this would go to another phosphorus. And then I could continue on this polymer and make a strand of RNA. Now, let me write base here. That makes more sense. Yeah. Okay. And again, the bases for RNA are adenine, thymine. I'll look it up. I'll tell you in a second. Hang on. Yeah, so it's adenine, guanine, cytosine, and uracil. And DNA, it contains thymine. But DNA, right, is a different name. It's deoxyribonucleic acid. And the reason it's called deoxyribonucleic acid, and this is where I'm going to cheat. I'm going to copy this all over. Shift it to one side. So that's my RNA. And then I'm going to duplicate it. And push it over here. And then I'll make it a little bit smaller maybe. There we go. That. I'll do the same thing here. Make this a little bit smaller so it fits. So the difference between DNA and RNA is simply this. Hang on. That group is missing. That's the deoxy part. The number 2 oxygen is missing on DNA. But the structure is essentially the same. It has a base, and it has a deoxyribonucleic acid. Right? Deoxyribose is what this is here. Missing the oxygen on the number 2 carbon. So that's it for this chapter. Again, if you have questions, feel free to send me a message.